Up here? The origin of the universe and string theory. This is stuff that I don't expect you to fully grasp, but we should probably talk about it if we're talking about astronomy. Where did everything come from?
The Big Bang.
Well, the Big Bang Theory says that the universe expanded from a point. And expanded and got larger and larger, right?
Mm-hmm.
Right.
But where did the point come from? Nobody really knows. But there are some ideas about how, see, the biggest problem that we have understanding where the universe came from is how do you get something from nothing? If there's nothing, how could something all of a sudden happen inside nothing? And so there's some thinking, there's some modern ideas that are going around in the heads of a lot of really smart people about how this could possibly happen. And let's just do a thought experiment. This is just kind of an idea how you might be able to get something out of nothing. First you have to imagine what nothing is. Can you imagine nothing for me? Let's imagine nothing. Are you imagining nothing? A lot of people would agree that empty space is a good representation of nothing. Would you agree with that? I'm not talking about space with some atoms floating around in it, but just completely empty space. Is that close to nothing in your mind?
Yeah.
A lot of people would agree, yes. Close to nothing. And so what I want you to do now is I want you to imagine a cube of completely empty space. Okay? An area of empty space. For example, this cube. Nothing in it, nothing at all. Well, what does the empty space have? The empty space has dimensions. It has height, it has length, and it has width. This imaginary piece of nothingness that we've imagined has dimensions. And scientists say, what if those dimensions could become something? And this is where we get into something called string theory. Have you ever heard of string theory? Have you ever heard of string theory?
I've heard of it, but
Heard
I
of
don't know
it?
what it is.
Is that like is it like some kind of way that the world might work?
String theory is the idea that there are very, very tiny one-dimensional strings that vibrate and create, their vibrations create all the different particles and energy that there is in the world. Let me go back to the dimensions thing. And we'll talk about what these dimensions things have to do with string theory. You could imagine me holding a string like this, right? A piece of, this is just a piece of dental floss. Now imagine I was holding it here. Imagine it was much smaller than this. If it was much, much thinner than this, could you imagine where it could get so small and so thin that you couldn't even see it? But it's here, but it's just so small you couldn't see it. Could you imagine that?
Mm-hmm. No.
If I take this really thin piece of string and I roll it up into a little ball, though, even if it was really thin, once I roll it into a ball, get it into a ball, even if it was really thin, if I rolled it up, a long enough piece of it into a ball, then you could see it when it was rolled all into a ball, even if it was really thin and you couldn't see it to start with. You see what I'm saying?
Yeah.
If I bunched up the string, you could see it. It's a little thing there. But when I straighten it out, it's so thin that you can't see it. Make sense?
Yeah.
Where we are so far? Well, imagine that the dimensions are like this. That height, length, and width could somehow be balled up to create something, to create something visible. This isn't just an idea. This actually happens in our universe. Do you remember a black hole?
Yes.
A black hole is the dimension of space pulled in by gravity and wrapped up around itself. And it's wrapped around itself so tightly that something traveling through it cannot get out. It just goes around and around in circles, pulled in by gravity, and cannot get out away from the singularity. Eventually it falls into it. And so a black hole is actually what we're talking about here. A black hole is coiled up, is dimensions that are coiled up so tightly that nothing can escape from it, and it's this black area of space. Well, scientists think that maybe dimensions themselves could somehow become wrapped up. And maybe that, what the dimensions wrap up into, are the subatomic particles that make us all up. The protons, neutrons, and electrons. We've found that protons, neutrons, and electrons, at least protons and neutrons, are actually made of smaller particles called quarks. Have you ever heard of that? A quark is a tiny particle that makes up protons and neutrons and electrons. But what are the quarks made of? And how small can you keep getting? Scientists think that maybe the fundamental particles of all could be coiled up dimensions. And that makes up all the matter and the energy too. Maybe energy is made up of coiled up dimensions too. You coil it up, they make something you can see, and if you straighten them back out, you have nothing again. Because when you straighten it out, you can't really see it. It's like nothing. But when you coil up these dimensions, you have something. And that's kind of what string theory is. String theory is the idea that there are little tiny one-dimensional strings. One-dimensional strings that can vibrate. That can vibrate and have certain waves, kind of waves going through them. And if they have a certain type of vibration, they produce, say, an electron. If they have a different type of vibration, they produce, say, an up quark, which is one of the types of quarks. If they have a different type of vibration, they produce a strange quark. There's a bunch of different types of quarks, and we aren't going to get into this in this class, but if you take quantum mechanics, you learn all these different types of quarks, and the quarks end up making things. A certain vibration of the string, and you have a photon. A different vibration of the string, and you have an electron. You might have some sort of gamma radiation with a different vibration of the string. So what string theory is the idea that there are tiny one-dimensional strings, possibly could be made up from dimensions that make up everything that there is. And it's the vibration of the string that determines whether it's matter or energy. And this picture here is showing some of the possible vibrations of these one-dimensional strings. They're so very, very tiny that there's no way for us to know if they even exist. They're smaller than the smallest atom, smaller than the smallest proton. These strings, if they're correct, they're so small we have no way of detecting them. So why do they think they might exist? Is because the laws of physics, and once you start doing the mathematics to figure out all the different laws of physics, that points to the idea that there might be these little strings. You want to see video footage of it?
Yeah.
If string theory is correct, by the way, there are not just three dimensions of space. Y'all know how we have three dimensions of space? Length, width, and height.
Yeah.
If string theory is correct, there's likely 10 dimensions of space, not just 3. Let's talk about first, before I show you this video, what a dimension is. What is a dimension? Well, a point in space is a zero-dimensional object. A point doesn't have any dimensions to it. It doesn't have length, it doesn't have width, it doesn't have height. But if you can move that point in one direction or another, you now are moving the point in one dimension. That's a one-dimensional, a line is a one-dimensional object. Now, if you could move not only this way along the line, but if you could move this way along the line, now you have what's called a flat plane. So you get more freedom of movement. You're moving in this dimension, now you can also move in that dimension. And now you can go anywhere in this area. This is a two-dimensional object, like a flat piece of paper, or this board is a two-dimensional object. If you add a third dimension, you can come out of the board and go out this way and come out into space. Now you've got the dimension of length, the dimension of height, and add the dimension of width. Now look at all the places you can go. Einstein said there's a fourth dimension added to length, width, and height. The dimension of time. You can go forward in time. You could theoretically go backward in time, but we've never seen anything do that. But maybe it could happen. But not only do you have the dimension of space, but you have this dimension of time. So that makes 4 dimensions that exist in our universe. Length, width, height, and time. If string theory is correct, there's actually 10 dimensions of space and the dimension of time. 11 dimensions. Where are all the other dimensions? Maybe some of them are coiled up and are making up all the stuff that we see in space. Making up energy, making up matter. And if you were to uncoil them and straighten them all back out, you would be left with nothing. Whoa. Let's see, you want to see video footage?
Yeah.
You're starting to get an idea of what string theory
Modern
is.
physics is dominated by 2 camps. The first upholds Einstein's relativistic model of the universe, an improvement over Newton's immutable mechanics which stick to a universal clock and could accurately predict all events. The other support...
Hold on, let's start over.
Modern physics is dominated by 2 camps. The first upholds Einstein's relativistic model of the universe, an improvement over Newton's immutable mechanics which stick to a universal clock and could accurately predict all events. The other supported quantum mechanics, which describes the weirdness at the subatomic level and whose major tenet is that both location and energy of a particle cannot be known without an inherent degree of uncertainty. Relativism and quantum mechanics are reliable and mutually exclusive theories that share a major problem. Both can't be right, and neither describes the overall universe or explains gravity. Enter string theory, a new model for describing fundamental particles and their behavior from the microverse to the macroverse. It could really be a component to the theory of everything. Like the unification of light, electricity, and magnetism, so too should gravity be combined. But grand unification hasn't been possible until string theory, which appears to be able to link not only the gravitational and electromagnetic forces, but also the weak and strong nuclear forces. It states that the fundamental constituents of reality are super small strings of the order of the Planck length, about 10 to the negative 35 meters, which vibrate at specific resonant frequencies. Any particle should be thought of as a tiny vibrating object rather than a zero-dimensional point. Like notes on a cello string, vibration modes produce different particles, electrons, photons, and perhaps gravitons. Strings can split and combine, appearing as particles emitting and absorbing one another, and explaining the standard model of particles. If the theory is right, it carries the promise of more dimensions than the 4 space-time dimensions with which we are familiar. These tightly curled dimensions are undetectable since they are smaller than the Planck length. There were different versions of the string theory, depending on the type of string and whether or not supersymmetry is incorporated. Despite the specifics, 5 theories emerged, each with the same concept but differing mathematical models. They were different flavors of the same thing and are collectively referred to as M-theory, because there is no known way to probe distances of the Planck length. Experimental verification of these strings remains daunting, but exciting new prospects to verify supersymmetry and indirectly detect the curled-up dimensions might rewrite the universe.
Wow.
Modern physics is dominated by 2 camps.
Wow, no. Did you follow any of that?
Yeah.
It's hard to understand this stuff because no one understands it. This is what's called theoretical physics, which guys that are really, really smart and know a lot of math sit around and play with equations, and then when they come up with things in their equations, they try to explain what they're seeing to people who don't know the math. And that's very difficult to do. It's like trying to explain calculus to a third grader. Yeah, it's not going to... they're not going to be able to follow very easily. Let's talk about what time is. There's lots of thoughts on what time is. Time is strange. It only seems to move in one direction. Not like these other dimensions. In these other dimensions, you can go right, you can go left. You can go up, you can go down, you can come out, and you can go back. But time only goes in one direction. You can only go this way, it seems. You can't go the other way. And most people, when they think about time, usually the question is asked, okay, if the Big Bang happened, what happened before the Big Bang? What happened? So you're talking about time there. When you say what happened before the Big Bang, you're talking about time, right? Well, it's weird because time is part of our universe. And these physicists think that time did not come about until the Big Bang happened. There was no time before the Big Bang. So the question doesn't make sense in the fact that time only came into being when the Big Bang expanded. Yes.
Is this Big Bang? Is this just for the Milky Way? Is that what it is?
The Milky Way is part of the universe.
But the Big Bang is like
the
every
Big
galaxy.
Bang is everything.
Every galaxy. Okay.
Every galaxy and all of space and all of time was born in the Big Bang.
Okay.
And all the other, according to string theorists, all the other 7 dimensions that we don't know what they are would also have come about at the point of the Big Bang. So we don't really understand. It doesn't really make sense to ask what happened before the Big Bang because time didn't start until the Big Bang. And so it's kind of an odd question to ask. Now, some scientists think that time, since, do y'all remember what it was like to have a closed universe? Y'all remember when we said the universe might be closed, what that meant? What'd that mean? You're nodding.
Yeah, you could be at one point, and if you go in one direction for a certain amount of time, you can eventually go back, be in that same spot.
You come back to the same spot. That's what closed means. A closed universe is like our globe. If I start walking in this direction, theoretically, if I could walk 24,000 miles that way, I'd be back here. It's pretty amazing, but it happens because the Earth is round. Theoretically, if we have a closed universe, I could fly off in a spaceship that way, and billions of years into the future, come back to this same spot if the universe is closed. Gravity wraps the space around itself, so you come back to the same point. If time is closed, like the universe might be, then if you head off in this direction in time, maybe you come back to the same part billions of years later. And so time is a closed loop also, like space. That's what some theoreticians think. If I head in this direction in time, I'll just come back to the same time period a lot later. And so time is a closed system, that there's no start and there's no end. It'd be like saying, where's the start of the Earth? There is no start to it. It's a ball. And just like it doesn't make much sense to fly off in a spaceship in this direction and come back to the same spot, but it could definitely happen if there was enough gravity. It doesn't make much sense to go off in time in this direction and come back to the same spot. But if time is closed, like every other dimension might be, then that's exactly what would happen. There's no start or end to anything. It's a big loop, closed loop. Isn't that weird? Is this freaking y'all out?
Yeah.
This is mind-blowing stuff.
So would time be in the universe? Could you accelerate to where you go faster than time?
You can go faster through time. Do you remember how when we did relativity, as you start going near the speed of light, time slows down for you?
Right.
So you can go, we know that you can go forward in time fast. And if I'm going near the speed of light, time's moving so slow that I could actually travel across the universe in a reasonable amount of time, because I'm going so near the speed of light. Time slows down for me, so not much time will pass for me as I'm crossing this huge distance. We don't know how to go backwards in time. We don't know if there's a way to do that. Nothing seems to go backwards in time. There's a theoretical particle called a tachyon. Y'all ever heard of that? A tachyon is a theoretical particle that travels backwards in time. And why does it travel backwards in time? Because it's going faster than the speed of light. Theoretically, if you could go faster than the speed of light, you would be going backwards through time. There was this cool science fiction movie that I saw that people from the future were communicating with people in the past through a tachyon radio. I don't know how they made a tachyon radio. People in the past were picking these signals up on their radio, and it was coming from someone. And at the end of the movie, you find out that they're way in the future.
Is it Land of the Lost?
What was that? No, it wasn't Land of the Lost. Yeah.
So if time is closed and I could live forever, that means that like I could sit here and like watch like the dinosaurs
come back, and eventually, if you lived long enough, you would come back and see the dinosaurs starting.
So we could see our universe being born again.
Forming. And one thing that's in this same some of these same ideas, they think that the universe is expanding right now. What if it were to slow down, stop expanding, and then start going back, and eventually come back to a point, and then do that again? They call that the big crunch, when the whole universe comes back down to a point. And that's one idea, that maybe the universe will do that one day. It's expanding now, maybe it'll stop its expansion and come back.
What would make it do that, though?
Well, scientists at first thought gravity might make it do that. If there's enough stuff, gravity could slow down the expansion and pull it back. But what we know now from looking the measurements we made is that the expansion of the universe isn't slowing down. It's speeding up. And so we don't know why that is, and if that continues, then the universe isn't going to come back down. But we don't know if that might continue, or maybe that'll stop. Yeah.
It might be like the planets, like the supergiants, like when they get to that certain point, they start expanding like really fast, and it might just at some point the gravity can't hold itself, and it'll just drop
and it just
down,
collapses
like, really fast, like it did last.
And blow up again, maybe, and restart the whole universe. We don't really know what's going to happen. That the idea right now is that the universe will continue expanding forever, and eventually all the galaxies will be so spread out, and eventually all the stars will quit burning and blow up and lose all their mass, and all that stuff will get just so spread out you won't form any new stars. Trillions and trillions of years down the road, there will be no light, and that will be a dark universe. That's what would happen if the universe keeps expanding. But if it comes back, that makes it a whole different story. Yeah.
So if the universe keeps expanding, why would there be no light? And also, could we be in a giant black hole?
Well, I don't know about the black hole thing. You'd think if you're in a black hole, then you're in a singularity. That's what's in the middle of a black hole.
Right.
And that's where everything's compressed into an infinitesimally small dot. So that we would be in a giant black hole doesn't, I don't know if that's actually happening. It would seem like everything would be small. But your other, I forgot what was the first thing you said.
If the universe kept expanding, why would everything go dark?
Oh, okay. So if the universe keeps expanding, then all the galaxies get spread out from one another, right? And so there'd be no nearby galaxies to see.
Right.
All the stars in the galaxy, stars are made from those big clouds of gas that compress to form a star, and then the star burns and blows up. Mm-hmm. But every time it does that, it uses up the hydrogen and the helium and creates these heavier elements. And pretty soon you'll get to elements that will no longer come together and form new stars and fuse.
Right. So
at that time there will be no more stars and there will be no more light. And you would just be left with a dark universe. They think that's possible, but it would be trillions and trillions of years down the road. But if indeed time is infinite, then even trillions and trillions of years will just be a blip in the entire timeline of the infinite universe. And it will just be a small portion where there was light, and the rest is darkness. Now, there's something else that you need to know. It's called the Anthropic Principle. The Anthropic Principle is the idea that the universe has to have factors that will allow us to exist. And, for instance, if gravity were a little stronger, then our universe would cave in on itself. It wouldn't expand. It would be pulled back really, really strongly by this stronger gravity, and the universe would collapse back to a point. If gravity were a little weaker, the universe would expand much faster than it is, and it would fly off in all directions, and we would have never existed. Atoms would not come together to make stars. The gravity has to be a certain amount for us to exist, or the universe would have never made it this long. So scientists wonder, how could gravity be this perfect number where if it were a tiny bit higher or a tiny bit lower, it changes the whole universe? And what scientists have come up with is a hypothesis called the multiverse hypothesis, where there's not one universe, but there's a bunch of them, and each little circle here represents one of the universe. And each universe has different properties. Some universes have stronger gravity, and they pop into existence, and then they immediately collapse on themselves. And people, living things, could never exist in that one. And another universe has different properties, and it might expand and get huge real quick and just fizzle out real quick. And there's all these different universes with all these different properties, and then one happens to pop up with the right properties that we can exist in it. And here we are. We're in that universe. And there's maybe a bunch of other universes outside our universe that don't have the right properties, but obviously you wouldn't exist in those because they don't have the right properties. So we call that the multiverse hypothesis, that there's many universes out there. And that's kind of mind-blowing. Maybe ours isn't the only universe.
Wait, so it's like, is everything just kind of based off what we know? Like, what if it is another universe with different properties and living organisms?
It could be a universe with different properties that does
that we
exist
may not be able
and
to
has
live.
totally different organisms.
Yeah, that we may not be able to live in.
Totally
Yeah.
different laws of space and time. Time might pass different. Space might look different. There might be more dimensions or less. And maybe if we were put there, maybe we wouldn't be able to survive. Maybe our atoms would just come apart in their different universe. But it could be out there where it's just a totally different universe, totally different properties, and totally different organisms if they did exist. It's kind of cool to think about. There's a theory called Mtheory, which they talked about in that video just for an instance. It's also called brain theory. And the idea is there's these big membranes. The reason why they call it M-theory is it stands for membrane. Do y'all know what a membrane is? Like in biology, you have the cell membrane. Remember that? A membrane is like a flat sheet. You can almost think of it like a piece of paper. So here's a membrane. Here's a membrane. And they think there might be big membranes out there that represent universes. And this is one universe with its dimensions, and this membrane is another universe with its dimensions. And when the membranes touch one another, boop, when the membranes kiss one another, it imparts a lot of energy from one membrane to the next. And again, it's mathematical equations and laws that point physicists into this direction. But they've calculated that these giant membranes when they touch, they might touch, imagine this membrane bowed outward a little bit, and this membrane bowed outward a little bit. They might touch at a point. And if the membranes have the right properties and they touch at that point, at the point where they touch, that could create a singularity that expands into a universe inside that brain. And they think that maybe that's where a singularity could arise from two membranes touching one another. And I don't really understand the theory very well either, but we call that brain theory. And sometimes energy or strings, like in string theory, can move from one brain to the other, which they show here, this string moving from one brain to the other. And there are strings in this brain, and there are strings in this brain, and sometimes the brains interact with one another. We call this M-theory or brain theory, and it's the cutting edge. It's trying to take string theory and put it together, put a bunch of different, there's a bunch of different string theories out there. And they try to put them together into one theory that explains everything. By the way, the theory that explains everything is called the GUT, which stands for Grand Unifying Theory. Scientists want to come up with a grand unifying theory, a single theory that explains everything in the universe. We don't have that yet. We have a nice theory that explains our normal space and time. That's called the theory of relativity. We have a nice theory that explains tiny particles. This is called quantum mechanics. But quantum mechanics and relativity don't go together very well, and scientists are trying to come up with a grand unifying theory that explains all of them, and string theory and brain theory is a candidate for a theory that might explain everything. It might be a grand unifying theory. Oh, here's what I was talking about. Two brains. Here's one brain, and here's another brain. When I say brain, I'm using like membrane, short for membrane. And the brains interact, and that could cause an explosion of a singularity into a universe in one of the two brains. Perhaps our Big Bang happened because of a collision between two brains. Let's take a look. Video footage.
Why is gravity so weak? Why can a small magnet pull or push something away from the entire Earth? There is an idea that may explain it. But before we go there, let's explore more preliminary ideas first. The most popular quantum gravity theory of today describes all fundamental particles as vibrating strings of energy. And the theory is constructed in a whopping 9 or 10 spatial dimensions instead of the 3 that we experience in our everyday lives. But what is a dimension? A line is a familiar geometric figure and can be completely described by giving its length. It is a one-dimensional object. It can be imagined that the dimensionality of an object can be created by taking an object of one less dimensions and moving it at a right angle to that dimension. You can create a line in your imagination by thinking of taking a point and moving it. Next, consider a surface. A surface is also quite familiar. The surface has both length and width and requires two measurements to define it, and therefore is a two-dimensional object. Similar to a generation of a line from a point, we can generate a two-dimensional surface by taking a line and moving it in a direction other than the direction of the length. And a solid figure is the stuff of everyday life. It has length and width and depth, and requires three measurements to describe it, and is a three-dimensional object. And like the generation of a surface from a line, we can generate a three-dimensional object like a cube by taking a square and moving it in a direction other than the direction of the length and the width. Cylinders, cubes, and spheres are three-dimensional objects. And now the hard part. The higher dimensions are created by moving a three-dimensional solid in a direction other than the length, width, or height. And while that is easy to do mathematically, it is impossible for us to picture it. So let's examine how we might detect these other dimensions. We begin with bright light spreading out in a spherical shell. The intensity of the light at any one point will fall off the square of the distance from the source, because the surface that the light covers grows as the square of the distance from the source. But that is only true in three-dimensional space. In four-dimensional space, the light will grow dimmer as the cube of the distance. And in 5 dimensions, it will grow dimmer as the fourth power of the distance. And in 10 dimensions, it will grow dimmer as the 9th power of the distance. Now back to strings. If this membrane represents the 3 dimensions that we live in, then particles like quarks and electrons are the strings that have the endpoints forever attached to those 3 dimensions. They might look like this. But the particle that is the force carrier for gravity, the graviton, is a closed loop. It has no ends that are constrained to our 3 dimensions. So if there are other dimensions, gravity will propagate freely there, as well as in our familiar 3. And that might explain why gravity seems so weak to us. We experience only a tiny fraction of gravity's true strength because so much of it is leaking out into other dimensions. But where are these dimensions hiding? One possibility, but not the only one, is that they're all around us, but incredibly tiny. If you look at a wire or a string from far enough away, it looks like a line, a one-dimensional figure. But if you get closer, or if you were a lot smaller than the thickness of a wire, then you would easily see that it has other dimensions. On the tiniest of scales, space has extra dimensions at every point. It might look something like this if we were small enough to see it. Accelerators like the LHC at CERN smash protons against antiprotons at enormous energies, perhaps enormous enough to produce gravitons. And if they do, then perhaps we might just be able to see them form in our limited 3-dimensional world and slip quickly and quietly away into those hidden dimensions.
Whoa. Did you understand any of that?
No. I fell asleep.
Well, I don't expect you to be able to understand this stuff, because nobody really understands it. But you should be able to read your book. There's like 6 paragraphs in this chapter that talk about these things: brains, dimensions, theories. And just have those ideas in your head, because when you go through life, you're going to be reading an article that says something like, the particle collider in Europe found evidence for gravitrons, or evidence for string theory. And you need to have some idea of what that is. If you remember this, oh yeah, strings are these little tiny things that might make up everything, then you'll be able to make sense of what they're talking about in these large colliders and stuff, even if you never become a physicist or anything like that. Some of you might become physicists, so you never know. You might be dealing with this stuff. You might figure out the grand unifying theory. If somebody comes up with this, they will be bigger than Einstein and Hawking and Newton, and they will be the new number 1 guy or girl. It'll be interesting. We'll see if we live to see it. Thank you.
Let's end it up.